Tiny desk?
Wait, so if the x value is 0 and it's 1, then where do I put the lines? On the. Okay, so for this one, x is 0 and y is 1, so did they go sideways?
Antiderivative.
On 0,
What's the function?
y minus x.
I totally spelled that wrong.
So 1
So it doesn't go up right here. Horizontally?
Oh, okay.
Yeah, so
Right,
right here.
0.
So my compound is right here.
You did it. Oh yeah.
That was
Kind
kind of upset right now.
1 minus 0. 2
I was like,
It's not.
okay, so we're gonna start with taking the derivative of functions because we haven't done that in a while. So the first thing we're gonna do is we are going to differentiate y equals 4x squared plus 6x plus 3.
That's it.
You'll see what I'm doing in a second. Rotary, what's that gonna be? 8x plus 6. Anybody have any issues with that? Right, we just took the derivative as power rule. So then what if I gave you a different function? And asked you to take the derivative of that function? What's the derivative going to be, Lauren?
How are you like introducing the C?
8x plus 6. So how did it happen that I had two different functions that gave me the same derivative? Okay, so when we're taking an antiderivative, we don't necessarily know if there was a constant or what the constant would have been. So when we start taking antiderivatives in indefinite intervals, we need to start introducing a plus c at the end. You're going to hate it when I say that a lot. No, just plus, because plus a negative is minus. So if I have an integral of some function f of x dx, that is equal to its original function big F plus c. If you don't have the plus c on an indefinite integral, it is wrong. So this is our general antiderivative, yes.
So just a refresher, the little f is the derivative.
Correct. Yes. They can also be called families of antiderivatives because all the family members have a different constant, but they have the same base function. So what we're going to practice today is using that plus c in our antiderivatives and then solving for what c could be. I know, we're so excited. So we're going to start with a little bit of vocab.
There's a whole line for big. You have SAT today, right?
Yep. So we have just gone ahead and written the definition of a differential equation. This is an equation involving a derivative. We also noted that the order of the differential equation is the order of the highest derivative involved. So when I talk about the order of a derivative, the first order or a first order derivative is simply the first derivative. A second order derivative is the second derivative. A higher order derivative then could be 3, 4, 5, 6, 7, 8. Every time we take a derivative, we increase its order. That is kind of useless information, but so a second derivative would be a second order derivative. A fourth derivative would be a fourth order derivative. Yeah. So what we're going to do right now is we're going to practice finding the general antiderivative for an indefinite integral I've been given at a specific point. Yes. They're the same notes we used yesterday, which is the first part.
Wait, so is this gonna take a lot?
Yeah.
Is this the Euler
Yes, this is Euler's method.
method?
It's okay. Everybody pronounces his name wrong. It's a last name. How can it be spelled wrong?
So this is just the first part?
This is the first part of the notes, yes.
You're gonna tell me you is pronounced toy. You're wrong.
Is it like French or something?
Euler, I actually think he's not French. I want to say he's like German.
Well, I'll look it up after.
How is it spelled?
Euler. Euler.
Yeah, I would say that's German.
He's actually a huge contributor to everything that we do in calculus. He's one of the founding fathers, I guess you could say, of calculus. Him, Leibniz, Newton actually did a lot with calculus as well.
Newton's already good.
Okay, so we're going to start with a general antiderivative. So if I have the derivative secant x tangent x minus e to the x, I need to find the antiderivative of that. So just like normal, I need to think about what gives me the derivative secant x tangent x.
See,
I just heard two things, I think. What is the antiderivative to secant x tangent x? Secant. So my antiderivative was secant of x. And then what gives me the derivative e to the x? E to the x. So my antiderivative is secant x minus e to the x plus c.
Will it always be plus C?
Always plus c, yes.
Why
No, that's just y. This was y prime because it was our derivative. This is what it was before I took the derivative.
You know, like, if we have to solve it, are you gonna give us what C is?
I will give you points that will help you solve for c, yes. I will give you enough information to solve for c. We're not there yet. We're still practicing just general antiderivative with the plus c at the end.
Are we gonna be doing this?
Yes. It's really easy. Come on. Okay, so second one. You do. It's 5 questions. So given this derivative, I would like to find the general antiderivative. Of course, if you want to formally write this out, then this is the same as dy equals dx, and then we can integrate both sides. But it's all the same thing. We're just taking the antiderivative of that entire function. So do that on your own. Take the antiderivative of that.
I feel like tell us what first thing that is.
I will tell you when we're ready for the answer.
Yeah, but is that a long one? No,
That would not be a log.
Oh,
Damn.
1 over x would be a log, and not 1 over the square root of x.
it means the square root of natural long.
Oh,
Sign.
Wait, was that it?
Okay, Deanna, I heard the first part of this. What is the antiderivative to 1 over the square root of 1 minus x squared? Sine inverse. Good. So that was this portion. Now we just need to find the antiderivative of that portion. That one's not a special one, so you need to change that into a fractional exponent. Move it up to the top and then just power rule it. What do you say? Yeah, so it's going to be minus 2 times the square root of x. And then what are we missing at the end? So anytime we don't have numbers or variables on that integral s, we have to have a plus c in our answer. I do think that we need to go over this though, because a lot of you seemed really confused. So that would be 1 over the square root of x, which is the same as x to the negative 1/2. And then when I reverse power rule it, I increase this by 1, so it becomes x to the 1/2. And then I have to divide out the 1/2, which means it flips and becomes 2x to the 1/2, which is 2 square root of x. Make sure you do know how to do that. Are we all okay with those two so far?
Yeah.
Anybody super duper confused?
Not yet.
Okay, let's do another one. Formally writing, this turns into the integral of dy equal to the integral of cosine t times e to the sine t.
Is that not chain rule?
Huh?
Is that not chain rule?
That is chain rule, actually. That should be a dt. I don't know why I put dx. So this is something new to you, which is why we're just doing a couple examples where we have to use this, because it's going to blow your mind. So Liam noticed that this is a chain rule problem because I don't just have e to the t here, I have e to the sine t, which means sine t was plugged into my base e function. The way we get around doing this, because this is absolutely horrendous to try and figure out myself, is we use something called u substitution. So u is going to be whatever my inside function is here. So here, that means that u is equal to sine of t. Since I know what u is, I can also figure out what the derivative of u is. So I can find out what du is. What's the derivative of sine of t? Cosine of t and then dt, indicating that I took the derivative. What we need to make happen is we need to make sure that this is present somewhere in our derivative function. And once it is, we reorder it to make it look exactly like this. So what I'm going to do is rewrite this as e to the u, because I replaced sine of t with u, times cosine of t dt. I just moved this cosine of t so it was next to this, so it matched this exactly. Once it matches, I can replace it with du. And that allows me to very easily take the derivative of e to the u, or the antiderivative of e to the u, which is no different than the antiderivative of e to the x.
What? Oh.
What are you thinking?
We're anti-deriving the sine of t, aren't we? Would that be negative cosine?
No, because the derivative of sine is cosine. Sine was our original function, cosine was the derivative of the original. So we're not anti-deriving the cosine because it was part of my derivative. We're only anti-deriving the sine.
Yeah. Is
And that's the derivative.
Cosine, negative sine.
Okay, hold on. Let me get to this and I'll show you what you are missing. Okay, so once we do the u substitution, we replace the inside function with u, we find its derivative and replace it with du. Then I can antiderive this, which is no different than e to the x dx. So what is the antiderivative of e to the u? E to the u, which means that my original function was y equals e to the u, but I know u actually didn't exist in my original function. So this is where I can plug that inside function back in. And that tells me that my original function was y equals e to the sine t. And then I have to have the plus c on the end of it.
What did we do with the?
The cosine disappeared because it was part of my derivative. So when I antiderive, the derivative part goes away. So now what we're going to do as a practice is we're going to take the derivative of e to the sine t. So you can see that that cosine never existed in the original function. It was an addition that was put on when I took the derivative. This is the hardest part to grapple with when it comes to chain rule and reversing it, is that we have new stuff in there that wasn't originally part of my function. It was a derivative that disappears when I take the antiderivative.
We also had the cosine in the original function that we were antideriving.
Which was my derivative function, so the original function didn't have a cosine in it, it had the sine in it.
Oh.
That's the part that you have to wrap your head around,
Okay.
is that this was not originally in my function. That was put in there because I took the derivative of sine, which means when I antiderive it, we kind of like suck it back up, like it never existed, because this is what my function originally was. That is the hardest part to grapple with u substitution. And that's why I'm only introducing it today and it's not on your homework.
Will it be on our quiz?
When you have a quiz, yes. So how, for the most part, do we kind of see the process for the u substitution and how we move stuff around? We're going to do one more u substitution, then we're going to move into the next part of the notes. I'm trying not to overwhelm you, but I wanted to introduce it.
So basically, it's just going to be another
It's going to be another what?
F quiz.
Oh, stop it.
You think I'm kidding? I haven't passed one test.
Let's do another one. This is the last one with u substitution in it. No, but today.
It could be. You get all throughout the class.
Just-
So when I'm given the derivative like this, I go ahead and rewrite it as an integral. So this is equal to the integral of dy equal to the integral of 4 sine v cubed times cosine of v dv. And then I can start to anti-differentiate.
Why do you have to write it like that?
Because that's the formal indefinite integral.
You have to write it like that.
You should, yes. If you can do it all from here, technically I'm never going to say no. But when you get to the u substitution, it's much easier to do the u substitution here.
Change anything. You just put a line in there.
Yeah.
I didn't change anything yet. I just rewrote it as an integral. That's all I did. So now I need to anti-differentiate this. I already notice that I have an inside function and I have an outside function. Because there's parentheses, which automatically indicates that whatever is inside the parentheses is an inside function. So my inside function here is sine of v, so that's going to be my u. Which means I need to figure out what the derivative of u is going to be. What is it, Tiana? Cosine of v. dv. Yes, good. Got to make sure you indicate that we took a derivative in there. So now what I'm going to do is I'm going to replace, after I move some stuff around if needed, I'm going to put the u in and I'm going to put the du in so we can see better what's happening. So this turns into the integral of 4u cubed. This is already grouped together and it directly matches what my du needs to be, so I can go ahead and replace that with du. And it makes it a lot easier for me to anti-differentiate that. Because now that looks like a power rule function. And I know what to do when I'm anti-differentiating a power rule.
Why?
So that is the same as 4x cubed dx. How do I take the antiderivative of that?
Where did the cosine?
The cosine disappears because it's part of my derivative, not part of the original function. This is the hardest part. Okay, so let's focus on this part. What is the antiderivative of 4u cubed du? U to the fourth,
Just use the form.
right? Because when I antiderive, I'm going to get 4u to the fourth, and then I divide by the 4, and that just gives me u to the fourth. U was not originally part of my function, so I need to put in what u was, and that was sine of v. Yeah, I'm pausing, sorry.
Make sure my kids never go on the honors track so they don't want to kill themselves.
Once you get the hang of it, it's really not too bad. But it is very difficult at first, and I know that.
You said
And this is
about
also still
everything.
kind of a simple.
It is. I always start simple.
What if your kids are geniuses?
I don't care.
So this should be what your general antiderivative is, because I replace the u then with the sine of v that I originally was, and then I have to put the plus c on it.
So the du, that's
Yes, because it wasn't originally in my function. It was the derivative of the inside.
The d just means we have a derivative. Taking the antiderivatives. That makes sense.
Okay. Are you sure?
You're saying the du.
How many more examples?
Yeah, so the
Yeah.
du is all derivative, so it disappears when I
That makes
antiderive.
sense.
Yeah.
Yeah.
Okay.
I don't understand why we took the derivative, but that's cool. Like, I don't understand why
like, why do we even write it there?
The only thing I understand
Because
is
we
that you have to
didn't
add
need it.
Because we have to locate, because, okay, so when I take chain rule, I take the derivative of the outside with the inside the same, and then I multiply by the derivative of the inside. So by doing this du thing, I locate what the derivative of that inside was, so I can eliminate it when I anti-differentiate, because it wasn't originally in the problem.
Now is you always first?
Yeah, we always find u first.
No, I mean like in the equation is you always first.
I think I'm confused by what you're saying.
Like sine v is in front.
Yeah, so u equals sine of v. Oh, okay, I see what you mean.
Yeah.
No, sometimes this will be in front. That's why we rearrange so that exactly what our du is present in here.
Now is that just dv
Because in here I took the derivative of v's. That's why that's dv. So that's why I replace it with du because I have u's present then.
So have we ever done a chain rule derivative thing?
Oh yeah, we did lots of chain rule derivatives.
I don't remember how we just all
We definitely did, because that was like the long one.
Yeah,
We
that
did it
takes forever.
over that week of like,
Indiana was killing it. She's like,
I was, because I actually understood how to do that.
So again, I know this is hard and it's gonna take us a little bit to wrap our heads around it. So that's why I wanted to introduce it today and then we'll move into a super easy part.
I kind of get it. You like take it out and then put it back.
Yeah, kind of.
More or less.
Yeah, pretty much. Okay.
You like it's weird. You like take it out and then change it a little bit and then write it back how it was originally. It's done.
Okay, so let's move into the next part here.
You know what? I understand.
She said no.
She's like, you know what? I'm just generalizing. Do I know what's going on? No, but yeah.
So what we're going to be doing now is solving the antiderivative function at a specific point. This can also be called the initial value problem, depending on who's writing the test. So they mean the exact same thing. It means you're going to take the antiderivative, plug in the values, and solve for C. That's all it means.
I need a nap.
So we're going to start with example A, which says that my derivative is equal to 2e to the x minus cosine of x. And y equals 3 when x equals 0. So we're going to start by rewriting that as an integral, and then we're going to anti-differentiate. So this becomes the integral of dy equal to the integral of 2e to the x minus cosine of x dx.
I can't.
Then I can take the antiderivative of this. What's the antiderivative of 2e to the x? 2e to the x. Super hard. What's the antiderivative of cosine of x? Sine. So this is minus sine of x. And then we had a derivative. This is the antiderivative, so no dx there. But we have to put a plus c. So I took the antiderivative and I put the plus c at the end to indicate a constant. Now all we have to do is plug in 0 for x and 3 for y and use that to solve for c.
Oh,
So then this becomes 3 equals 2e to the 0 minus sine of 0 plus c. E to the 0 is 1. 1 times 2 is 2. What's sine of 0?
1.
0. Plus c, 2 minus 0 is 2. Subtract the 2 over, and I get 1 equals c. So once I identify what c is, I take it.
Well, where'd you get that 3?
That's what y equaled.
I was kidding. I was doing it.
She's standing.
And I just go ahead and put that c in to my antiderivative equation. So that means the exact antiderivative of that integral with this point is this. That is my exact original function. That's what we're doing today.
that's as bad.
Well, I have a couple more examples.
How about one more? And you just see this one.
I have 3, 4, 5 more examples.
We're only doing one.
We're doing
Bye.
homework tomorrow.
Okay.
Give
because
us the
listen,
harder ones.
I don't even have SRT. We look at student council meeting.
Okay, well, we still have 20 minutes.
There's no way. Really?
There's
Yeah, but
plenty
I'm
of
gonna
time.
have to do the. I know.
have room for one
But I'm gonna have no time to do my
You
homework.
better make more room.
Or just only take one more example and watch them.
Well, no, I'm gonna do at least 2 more examples.
Give us the harder ones.
Let's do. Stop it. We'll do D.
I don't like it.
I'm putting it down as B, just because I don't like going A to
And you do it on the AP test, they will count you wrong.
Oh.
What do you
Oh,
want?
B. I thought you meant you were
Am I
replacing my S with an X.
Am I dyslexic or are you?
Actually, curving your thumb, it's a D.
You're fine. You're fine. Yes, make the D a B. If you're looking at the notes, this is example D for this. That's why I put that.
Yeah, I was scared. I was like, what do you mean? I was just putting it
No,
down.
sorry. I thought you meant you were replacing the S and the T with Y and X. You can't do that. Yes, you can't do that.
That's dumb.
I'm not lying.
Yeah.
My whole life, like,
Ridiculous.
ran shoppers.
It's just letters in the problem.
No, yeah, if they say DS and DT, you have to use DS and DT on the AP test.
Well, what if
Well, actually, it doesn't matter. Never mind.
Okay.
What if I use switch the variable, then at the end, I really.
If at the end you switch it back, you're probably okay, depending on who your grader is.
I'm gonna fight everybody who grades papers. because
Okay,
people-
so let's turn this into the integral first.
You didn't give us any points.
I will in a second.
Jeez, I'm thinking of
Oh, that's the wrong way.
I just wanna graduate, I'm over this crap.
Do it. Well,
How will we tell which one?
Oh, yeah, but you know,
and which one's S?
nobody listens to what
Well, the one in the function is your X. The one outside is your Y.
Oh,
It really won't matter, truthfully. Okay, when I'm presented with an integral like this one, it is actually going to be easier for me to simplify this before I try to anti-differentiate it. So I should multiply that t in first, because then it turns into a reverse power rule, which is a lot easier to work with. So that means s is equal to the integral of 3t squared minus 2t, and then dt.
So we put the DT after.
Well, the dt just comes at the very end, always. And then I can just anti-differentiate each of these terms separately. So that means S equals, what is the antiderivative of 3t squared? No, that'd be the derivative.
Whoa.
Antiderivative.
T to the third.
T cubed. What is the antiderivative of negative 2t?
T to the T squared.
T squared. And then we have the plus c at the end. This is my S. This is my T. Oh, wrong way. Dang it, I do that every
You're
time.
like, how are we
This
supposed
is
to know
why
that?
you use X1.
It says when T equals this and S equals that. I just shortened it because I didn't have enough room.
Okay.
So T here is 1, S is 0. I go ahead and plug those in. And then I solve for C.
Zero equals C.
No, 0.
Should be 0 equals C, which means when I go ahead and rewrite my antiderivative, I'm not going to have a C on it because the C is equal to 0. So my antiderivative equation is T cubed minus T squared. You can put plus 0 if you want to, but that's a little bit redundant.
Okay, so I got it. So after we find C, we put that in for C.
Yes,
We do-
in here. Yep,
Okay. But if, since it's 0, it's just the same.
correct. Yep. Okay, so we are going to do
Oh my god.
Oh my gosh, if we do E or F, if we're jumping off a cliff.
we're gonna do E, we're not gonna do F.
I would not.
That means I have to use a whole page.
We're done with this after today.
Oh.
When are we done with,
Right in the margins.
when are we done learning new stuff? Because,
We are almost done. We have U substitution and we have volumes by revolution and a couple little things that we can
That sounds
put in there. Oh, I hate it. It's the worst thing in calculus, truthfully.
So,
Yeah.
And then we're done.
so you hate it.
If I
but
don't
I'm
hate
not
my
good.
life enough.
I don't know why. I really hate volumes by revolution.
I like thinking.
I like math back in 8th grade when me and Dina just did nothing to do everything.
Yeah, that's Mr.
No, it's
Lopez.
nice.
No, Mr. Lopez was so easy. I had like,
Okay.
I didn't have to.
I saw once in algebra.
Yeah, I had
I
right.
have
And
a college too.
I got yelled at her kind of.
Okay. So we have this one.
At least it tells us what's even. So you might hate me after this one.
Both of you to see my job.
It's bad.
Wow.
She got PTSD from that. Calm down.
I'm just kidding. I love you. It was just funny.
It's exactly what my algebra 2 kid said.
I'm kidding. I don't know who.
Okay.
You know what's an algebra 2?
So we're talking
I
about
think
the
we already did
sophomore.
that, didn't we?
Yeah, you did already know it was
Yeah,
an algebra 2 kid. It's fine.
Well, I'll sit here for all of them. I don't care.
Or was it a sophomore then?
Sophomores or like middle?
Is it before or after the?
Was it my brother yesterday?
My sister
I'm
is
kidding. You don't even have my brother.
Oh, I hate everyone in class.
Your brother's gonna graduate with that.
I think so.
Liam, you should have graduated.
He's in.
Why would I want to do that?
I think he's in. I don't know if that's.
Wait, why do we put 0?
I'm showing you something
See,
new.
these are the ones, why? these are the
This
ones that
is
are-
Euler's method.
Euler, what
Is
the?
it the same thing as execution? I think we're losing geometry.
How do you know when you add?
Well, you add C at the antiderivative.
You
We
always
haven't,
add it no matter what.
Regular.
unless you have numbers on that. So here we're not gonna add, well, we will add C, just kidding. But yes. Okay,
I'm embarrassed.
I know, we're all super excited.
I want you to know I don't hate you. That was just a
I know. I kind of know. I'll put it that way.
joke. Whoa.
I kind of know.
I just hate this class. I don't hate you.
Okay, so Euler's method is kind of a shortcut. I personally don't like to use it, but I wanted to show it to you in case any of you do like it. So Euler's method says that du here is the same as u of x. And that is equal to the integral of 0 to x of 2 plus cosine of t dt. And then this can be rewritten in a very specific way.
Wait, where did you pull these X's and O's out of?
This is Euler's method. As I said, I personally don't use it, and I've never seen it on the AP test. Actually, I've seen it once, but it was a multiple choice question. It wasn't crazy at all. So Euler's method says that I can take this integral, add c to the end, and it's going to be my answer. But it's even easier than that because I don't actually have to solve that part out. I'm going to only use this piece of information. I know we love it, right?
What is going on?
Okay, so first thing we did, change this into u of x. It's just a notation change.
And that's c.
Equal to the integral from 0 to x because that was the variable I had. Change the variable inside of here to a t. You can change it to anything that you want to. It really doesn't matter. Stop. No, it wasn't a t, it was an x.
The heck?
So you change it to a t from the x.
I can only answer one question at a time. So what we did, I took this function, I integrated, I wanted a change of variable. So Euler's method says that since I had a u and an x here, I could make an integral that had a 0 and had my variable x, and I replaced that variable x here with a t. You could have made it an s, you could have made it an e, you could have made it anything. Don't make it an e. Could have made it an a, whatever you wanted to. Euler's method then says I can rewrite this integral in the notation u of x because that's what it was originally, and that is equal to the integral plus c at the end. And then I just solve for what u of x is going to be based off of this information, and that's going to be my overall answer.
Is C outside of the integral?
Yes. So I know that my x value here was 0, so u of 0 is equal to -3. So that has to be what my constant is on the end. So Euler's method says that if I do this change of variable, then my antiderivative is equal to that integral with that constant.
Why'd you have to change the variable?
Because that's how Leibniz and Euler's work. We plugged the variable in, so I did the opposite and pulled it out.
But we don't have to use this.
You don't have to use this. I just wanted to show it in case anybody really liked it.
I hate.
I personally would rather just anti-differentiate that.
That just made me weird.
I think I do like it.
Ow.
I don't get it.
So I pulled out this variable and put it here, left the integral, and then used that to evaluate for my constant.
So I don't have to antiderivative then?
Well, you still could eventually, but this is what it will be equal to, so this is a form of writing it.
Oh.
Yes.
So this is
That just seems like another step that you don't need.
Again, it's just a different method. We are done now. So your homework was all the stuff before this one. So A and D that we did here, where we take the antiderivative and plug in point values to find C and plug that back in. That's what your homework is.
that. I